This is Isaac, and
June.
we're here to show our video report for our energy transfer apparatus.
We will be answering several questions and showing how our apparatus works.
We will end with a live karate demonstration.
No, we will not.
Explain how your apparatus exhibits the transfer of potential energy to kinetic energy. Our energy transfer apparatus changes potential energy to kinetic energy in that when it starts, the marble has gravitational potential energy because the marble has mass and it is raised off the zero reference level, which means if there was nothing interfering with the marble, it would fall to the zero reference level, having energy. That changes to kinetic energy in that when we drop the marble, it starts moving, and when it's moving, it has kinetic energy. Explain how your apparatus exhibits the transfer of kinetic energy to potential energy. Our apparatus changes from kinetic energy to potential energy once the marble falls off one ramp and starts moving up a second ramp. As it's moving up the second ramp, it has kinetic energy because it's in motion, and once it reaches the farthest it'll move up that ramp and it stops for a fraction of a second, it has potential energy because it has height off the zero reference level. And once it starts to move again, that'll go back to kinetic energy.
Calculate how much gravitational potential energy the apparatus begins with. To do this, we use the equation of gravitational potential energy, which is Ug equals mgh. Then we found the mass of the marble, which was 0.005 kilograms, or 5 grams. We multiplied that by the gravitational constant, 9.8, and then multiplied that by the height of the marble above the zero reference level, which was 1.07 meters. We multiplied all of those numbers to get a gravitational potential energy of 0.05243 joules. With correct sig figs, this number would be 0.5 times 10 to the negative first joules. And that is the gravitational potential energy that the apparatus begins with. Calculate the speed with which the flag is raised. To do this, you divide the time it takes for the flag to raise by the distance the flag raises. The flag raises 0.453 meters total, and it only takes 0.67 seconds. Now, we divided these numbers to get 0.68 meters per second, which is the speed that the flag is raised. Was energy conserved? To answer this question, we use the fact that the sum of the energy before the event should be equal to the sum of the energy after, and the sum of the energies are potential energy plus kinetic energy plus radiant energy. Now, for the sum of the energy before, we know that the marble has no kinetic energy yet until you drop it, and no radiant energy. Therefore, we only need to solve for the potential energy of the marble. We already solved this 2 questions ago, and so our answer was 0.5 times 10 to the negative first joules. And that is the sum of all of the energy before the event. And now to see if energy was conserved, the sum of the energy after should be equal to this number. To figure this out, we will find the kinetic energy of the flag. So to find kinetic energy, we use the equation K equals 1/2 mv squared. First, we found the mass of the flag, which was 0.0008 kilograms, and the velocity of the flag, which we solved in the question before this, was 0.68 meters per second. We plug these numbers into the equation and multiply them out to get 1.8 times 10 to the negative 4th joules. As you can see, this number is significantly less than the sum of the energy before, meaning that energy was not conserved.
In our energy transfer apparatus, energy was not conserved throughout the entire thing. Some of the ways energy was lost was in the marble's friction against the wood. As the marble rode down each inclined plane, it rubbed against the wood that formed the inclined planes, and that caused it to slightly slow down, losing a little bit of energy each time. Another way it lost energy was friction on the pulleys. The pulleys, as the rope went over the nail, the rope had friction against the nail, causing it to slow down and lose a little bit of energy. It also lost energy from friction against the backboard. Almost everything that was moving, including the marble, the pulleys, and the flag, rubbed against the backboard. Every time anything rubbed against the backboard, it lost a little bit of energy due to friction. The next way the marble or the entire thing lost energy throughout the energy transfer apparatus was air resistance. As anything moved, there was a little bit of air it had to displace in order to get to its new destination, and each time it had to displace air, it lost a little bit of energy. The final way energy could have been lost during our energy transfer apparatus was through sound. Every time the marble or any moving part created any sound, that sound is energy in the form of sound waves. So each little sound was a little bit of lost energy.
Our energy transfer apparatus cannot be converted into a perpetual motion machine. This is because our energy transfer apparatus has multiple moving parts, such as the pulley systems which fall down. They cannot be reset with the energy we have throughout the apparatus, which means you cannot run it more than once. Also, we couldn't raise a marble back to the very starting point because that takes the same amount of energy we start with, and as the apparatus goes along, we lose some of that energy. This is why our apparatus cannot be changed into a perpetual motion machine.